All right, so we have come to the grand finale, problem 25C on the final exam practice. We want to find the distance from a point with x coordinate x naught, y coordinate y naught, z coordinate z naught to the plane with this linear equation ax plus by plus c plus d equals 0. We want to show that the distance is equal to this quantity here. Okay, so knowing that ax plus by plus cz plus d equals 0 actually tells me a potential candidate for the normal vector. And for all intents and purposes, this is the normal vector. So this is going to be the vector with components a, b, c, because those are the components I see in front of x, y, and z, respectively, in my linear equation for my plane. Okay, and so now I essentially just want to draw a picture. So here's my plane, I have my normal vector, n, and I know that this point is located somewhere, so I'll just pretend like this normal vector is pointing in that direction. It doesn't really matter how it looks, but for my picture I can just draw it like this. Okay, so this point is not on the plane, right? So it's anywhere outside of the plane, and so I can just draw it so that the normal vector is pointing towards it. So either way, how we'll make do with this is we need to find a point in our plane, so that what we can do is take, so here's my x naught, y naught, z naught, take the vector that points between this point in our plane and the point that we're interested in, and then we want to take the scalar projection onto the normal vector, and that will give us the distance. Okay, so what we're saying is that the distance is equal to the magnitude, so the absolute value of the component of this vector, whatever this vector is. I'll just call it v in this case. We don't have a vector v yet. So this is going to be v projected onto n, the scalar projection, and then we're going to take the absolute value of that scalar projection, and that will give us the distance to the plane, because this is a right angle. Okay, so either way, let me call this point here x1, y1, z1. And so knowing that x1, y1, z1 is a point in my plane, I know that it satisfies this equation, right? So I know that I have a x1 plus b y1 plus c z1 plus d equal to 0, right? Because this point is in my plane defined by that equation. Okay, so I'll save that for later. And this vector v that I'm looking at now, this originates at x1, y1, z1, and terminates at x naught, y naught, z naught. So it's going to have components x naught minus x1, y naught minus y1, and z naught minus z1. Okay, and so now going back to our scalar projection, I want to take the absolute value of this scalar projection. So my scalar projection is just equal to n dot v in the numerator divided by the length of n. I can compute the length of n fairly easily. It's just square root of a squared plus b squared plus c squared. So let's just figure out what this numerator is now. Okay, and so the numerator, n dot v, of course, an absolute value, this is equal to, well, I take ABC and dot it with x naught minus x1, comma, y naught minus y1, comma, z naught minus z1, and so I get a times x naught minus x1 plus b times y naught minus y1 plus c times z naught minus z1. Okay, and so this is just about the end of this problem, and the additional thing that we need to see is how to get this d back into our expression here. So we have an ax naught plus by naught plus c z naught. We just don't have this d. However, we do have this a times negative x1 plus b times negative y1 plus c times negative z1. And so if we go back to this equation, ax1 plus b y1 plus c z1 plus d, we see that d is actually equal to the negative of all of this stuff, right? Because if we subtract everything over here, we'll get that d is equal to negative ax1 minus by1 minus c z1, and that's exactly the remaining stuff up here. So this numerator turns into ax naught plus b y naught plus c z naught plus d divided by square root of a squared plus b squared plus c squared. And that gives us the distance from this point, x naught, y naught, z naught, to the plane given by the linear equation ax plus by plus c z plus d equals 0. And this actually generalizes our distance to a line a bit because, of course, we have any line we can put inside of a plane. Okay, so either way, slightly different problem, but a generalization of the idea. Okay, so this is our distance here, and we have come to the end. You have made it. Final exam practice is over.